Alright guys, let's get started on lesson 3, bacterial growth. So this formula we've already discussed, and hopefully you're getting more familiar, more confident with using this formula so that we can do these word problems and you'll be not having any difficulty with them. So total number of bacteria after a given time, NT. Variables don't matter. Sometimes you see this as A, T, sometimes you see it as any other variable. I can't think of one right now. So let's say we'll use the N as the number after a given amount of time. Original number is NO, original amount. Base is B. Now these are the two variables that I want everybody to work on and get figured out. Time elapsed. So many examples have word problems that say after 3 days, after 4 hours, after 7 minutes. So time elapsed, the word after is so often used in the problems that that's a big tip, that that's the T value. Now D value, they have to be in the same units. Really important if we're talking years, T and D are both in years. Minutes, they're both in minutes. So in this time, D is actually the time it takes for the growth or decay to occur. I sometimes refer to it as the official doubling or tripling or half-life given in the problem. And sometimes it's not given, sometimes we have to find that official time it takes for growth or decay to occur. So let's look at an example using a culture. It triples every 25 hours. So this first sentence gives us two variables right away. Triple means we have a base 3. So the number after a given time, original amount, well I know the base is 3. Now it says it triples every 25 hours. That's the D value, the time it takes for growth to occur is 25 hours. Making a note here that we have to be in hours, means our T has to be in hours if our D is in hours. Now it says if the initial amount was 1,000, that's NO. We don't know T yet, but this would be an equation we could use to solve for any amount after a given time. Let's do the next question. It says how many bacteria in 4 days? So hopefully this was a big hint to you that we cannot put 4 in for T. We have to change 4 to hours. So we do this and we get 96. 80 and 16 is 96. So we have our formula with 1,000, 96 over 25. And we don't have to graph that really. We can just go right to our calculators and plug it in exactly as it looks. Now with my old TI-83, I have to put a bracket around any exponent that's a fraction. If you have the TI-84, then you are in the exponent spot. You don't have to put a bracket around it. But as long as you're getting this answer, you know you're doing it correctly. Now guys, as you're listening to this, I want you to pause and try the next question without seeing my work and then see the answer. So it's important that you take your time and go through these. Try them before I do them, and then see how it's worked out, and hopefully that will help you understand it a little better. 3 days ago, that looks a little different. 3 days ago, again it's in days. We want hours. So we have 72, and we're going to put into the formula to get the number time elapsed. Well, this is ago. So what we have to do here is put the exponent as a negative. Picture this on a graph. If we put in a negative value for the exponent, we're going to go onto the part of the graph that's less than what we started with. So that makes sense because it's days ago. It should be less than 1,000. We can put this in our calculator the same way we did the B question and get an actual number without having to graph it. We just need to calculate it. All right, so that's a really typical question, changing the units to make your T and D values match and get a really clear feel for the values in that formula. Let's try another one. So changing formulas, but really not changing formulas, because this compound interest formula matches the growth decay formula. A is the value after a given time, not value anymore, but amount. So we're talking money, amount of money, but it's money accumulated after a given time has elapsed. So really same idea. P is the initial amount, which is the same as NO, the number original number. P is the original number called the principal now in compound interest. I is the interest rate. Notice that it's per compounding period. So if it's an annual compounding annually, then we leave I as the annual interest rate. But if it's compounded semi-annually, we would take our annual interest rate, divide it by 2. Compound quarterly, divide it by 4. If it's compounded monthly, we divide it by 12. Okay, we'll look at that in our example. Now, N is the number of compounding periods. So if it's compounded annually, N would just be the number of years that have elapsed. But if it's compounded semi-annually, then we times the number of years by 2, because that's twice a year. Compounding quarterly would be timesing the number of years by 4, because it's 4 times a year. So let's look at this first question. $1,000 investment, 8.3 interest rate per year. So this means per year. And interest rates are always given as annual interest rates. Now it's compounded semi-annually. So in our formula, what we're going to have to do is take the interest rate, 0.083, as a decimal, 0.083, and divide it by 2. Because compounding semi-annually is twice a year. So we have to divide the interest rate by 2. Now one other thing is the N value, which is the number of times it's compounded, is twice per year. So twice per year, T being number of years, would be the exponent. Notice that this divided by 2 and times by 2 always ends up being the same. If it was quarterly, we divide by 4 and times by 4. If it's monthly, we divide by 12 times by 12. So in your formula, the initial amount, starting with $1,000, see, these are the values that always match up. And it's increasing with the compound interest. We start with 1 plus because it's increasing by this percentage. Okay, now if we had to solve a question using this formula, determine how long it takes for the initial investment to increase to $1,490. So our A value is $1,490. Original amount is 1,000. And our equation would look like this. Now, we definitely wouldn't solve this algebraically. We would solve this graphing. What we would do is do y1, y2, so left side, right side. Change the window because these numbers definitely are way too big for our standard window. And you might have to play with this window a little bit. So I want you to try this before seeing my answer here. So get a good look at this graph. With this window, it looks great, but you could see this with many different windows. As long as you see that intersection point, second trace intersect, and you should be getting this answer. 4.9 years. It takes 4.9 years for it to reach 1490. Now we have to consider the rounding. When we're talking about compound interest, we have to consider the rounding, especially if it's compounded semi-annually. That means every 6 months the interest gets added on. So we would be looking at every 6 months increasing in the amount. So 4.9 years, if this question said to the nearest year, we would say in 9 years, it takes 5 years for it to reach 1490. But in some cases, we do have to consider, if it's semi-annually, which half of a year, if it would be rounded to 4.5 or 5 years. So we'll get to examples like that where we have to watch the rounding with compound interest questions. But this one, we could leave it as 4.9 unless it's said to round to the nearest year. Okay, let's look at a depreciation question. So we know with depreciation, the base is going to be less than 1. So between 0 and 1, what's the base going to be if it depreciates 15% per year? Well, you know what, this is so similar to our original formula with NT and NO. We're looking for an amount after a given time. Original amount is this, or original number, it's the same formula. Now the base, if it's decreasing by a certain percent, we talked about this already, if it's decreasing by a certain percent, we do 1 minus that percent. That's how much remains. So 1 minus 0.15 is 0.85. So whenever it says it depreciates by 15%, that means 85% remains per year. And T over D, this time it takes 1 year, because it says per year, to decrease by 15%. So the D value here is just 1. Time is in years, we could use T or X, but this would be our equation. So X over 1, we don't have to write in a denominator at all. What's the value of the car after 5 years? There it is. Original amount, 0.85 exponent 5. Plug that in your calculator. And then see if it matches this. So that's it for the depreciation, but really common problem with the exponent equations. So let's try one more. Half-life. Just the title of this, we know what the base is. What is the half-life of a sample of plutonium if it decays to 1/64th of its original after 30 hours? All right, well, the first thing that jumps out at me is that this is half-life, 1/2. What is the half-life? So the time it takes for it to decrease to 1/2, that is the D value, half-life. That's what the question's asking us. What is the half-life? That's our D, that is our unknown this time. Now, time elapsed, it says after 30 hours. So that word after that I mentioned before, there it is. After 30 hours is time elapsed. And that's going to be our T value. So far we have this. Now, we did talk about a question in assignment 1 or 2 that had how long does it take to triple? And tripling, we said tripling would be the division of the amount after a given time divided by the original amount. So the amount after a given time over the original amount would be 3 if it tripled. But this one is not increasing, it's decreasing. It decays to 1/64th of its original. So what that is saying is that the amount after a given time over the original, the amount after a given time over the original is 1/64. It decreases to 1/64th of the original. So now we can take both of these variables, NT over NO, and that cancels out both of them. This is a fraction of those two variables, and it equals right, now this one, we could do this one on our calculators, y1, y2 intersect to get the answer. But I recognize these values, 64 and 2, as a common base. I can solve this a number of ways. So depending on the question, if it was a written response question and it said algebraically, then I would want you to change it to base 1/2. And I know there was some people asking about changing it to base 2 or base 1/2, but you can do either. If I change this to base 1/2, 64, I want to check to make sure I don't make a silly mistake here. 2 exponent 5, no, 2 exponent 6 is 64. So 1/64 is the same as 1/2 to the 6. So there we go. Now if I wanted to change this to base 2, I could do that as well. I could make this 2. 1/64 is the same as 2 to the negative 6. And 1/2 is 2 to the negative 1. Both of these equations will give me the right answer. So if I was working with the 1/2, I would drop the base and say D is 5. If I was working with base 2, I would simplify, drop the base, negative 6 equals same answer. So many times you have a choice. If you're working with fractions, you can leave the base as fractions, or you can make your exponents negative. Okay, let's go back up and answer this question. What is the half-life of a sample of plutonium? So we got an answer of 5. The D is what we're looking for. The T was the hours. So now we have to answer it as hours. So the half-life of plutonium is 5 hours. All right, that's the end of lesson 2. We have, lesson 3. We have lots of time now to get ready for our first quiz. And that first quiz is on Tuesday. So you need to make sure that the videos with the notes are filled in. Videos are watched, notes are filled in, and assignments are completed. And hopefully in class we can get lots of the assignment work done. Okay, bye for now.